All right, so we are going to talk about regression and correlation. And you can kind of read through this information up here. We're going to talk about this relationship between two variables. If one variable has an impact on the other, or relationship, that is called correlation. Okay, and there's different types of correlations. We can talk about linear relationships, where if we plot the data points, it basically makes a line, okay? If the data points are really close together to the same line, that would be a strong relationship. If I draw a line and the points are kind of more scattered out, that is a weak relationship, okay? They still form a line pattern, but they're just more spread out. Some things have no relationship, and some things have like what's called a non-linear relationship, where it makes something that is not a line. In our class, we're going to study the linear relationships. Okay, so we're not going to worry about these non-linear ones until later on. Okay. All right, so if we have a linear relationship, I just wanted to review the equation of a line. If you've taken an algebra class, you might recall y equals mx plus b. Your slope is this number here, the m value. This tells us how steep or flat a line increases. All right, this b value is called the y-intercept. This is where it crosses the y-axis, and that's the axis going up and down. So this right here is the y-axis, okay? All right, we're going to talk about the independent or explanatory variable. This is usually the x value, okay? This is the variable that influences the response variable. Sometimes we call this the input. Okay, the dependent or response variable, this is a y value. Okay, this is the variable that responds or can change based on the input. We sometimes call this an output. Okay. All right, if the data points on a scatter point are all close to a line, then there is a strong relationship. If the data points are loose or more spread out, we call that a weak relationship. Okay. All right, so let's look at these examples. We've just got different scatter points drawn here, different scenarios, and we're going to circle the right answer choice, or I'm going to highlight here. Okay. All right, so we have hours worked, amount earned in dollars. So this is your independent variable, and this is the dependent variable. So the amount you earn depends on the hours you work. Okay, and that makes sense. Okay, so if I was to try and draw a line connecting these points, you see how they're all really tight together. So that means that's a strong relationship. Okay, so it's not B or D here. Okay, now if I'm going up as I read this graph from left to right, and I would be going uphill, then that is positive. Okay, so answer A there. All right. Okay, over here we have age and height in inches, age in year and height in inches. And we have this class here. So as I look at this data here, it's not really going up or down. Okay, so I would really say this is no correlation, no relationship. Okay, it's kind of straight across and all spread out, so I would say no correlation there. Okay. All right, for the next one, we have age in years and Honda cars value. So as your car gets older, it looks as though the value is decreasing. Okay, so this is definitely some sort of negative relationship. So now I just need to decide if it's weak or strong. These points are a little bit more spread out, so I would say this is more of a weak negative correlation. Okay. All right, next we have number of customers and temperature for this ice cream shop. All right, so if I was to try to connect these points, it would maybe look a line like this. That's definitely positive. So if they're real tight together, that'd be a strong relationship. If they're a little bit spread out, that's a weaker relationship. Okay. All right, so let's look at this example. We have age in years and vocabulary size for children. Okay, so as I just kind of look, as our age increases, so does the vocabulary that the children have. The independent variable is this age. A lot of times the independent variable is some sort of time. All right, so the dependent variable would be the vocab. All right, we're going to draw a scatter plot. So down here, I'm going to put the age, and up here, I'm going to put the vocabulary. So we've got 3, 4, 5, 6, 7, and 8. All right, going up and down. I need to get to 4,200. My smallest is 600. I'm going to count this off by 500s. Whoops, there's 1,000. So 1,500. All right, so let's see here. My first one is 3,655. So I'm going to find where I'm 3 years old and kind of estimate, I want that point above 500 but below 1,000. And then for my next one, 4, I'm above 1,000. Then for 5, I'm below 2,000. For 6, I'm around 2,500. For 7, I'm above 3,000. And for 8, I'm above 4,000. Okay, so if I was to draw what we call a line of best fit, ooh, that's off a little bit. All these points, first of all, this is going up, so this is a positive relationship. And I would also argue it's a pretty strong relationship. Those points are all pretty close to the line. All right, so instead of just saying strong or weak, in math we like to assign numbers to things so we can, be objective and not subjective. So this number we assign to that strength of a relationship is called Pearson's correlation coefficient. Okay, and we're going to use the letter R for that. Okay, so if R is -1, that is a perfect negative linear relationship. And that is a very strong negative relationship. Okay. If R is +1, then that is a very strong positive relationship. Okay, so R just describes how strong or weak it is. If R is 0, then there's no relationship or no correlation at all. Okay, if R is something like 0.25, we would say that that is like a weak positive relationship. If R was something like -0.90, I could say that's still a strong negative relationship. So this is kind of a scale from -1 to 1. R cannot be bigger than 1 or less than -1. It's got to be between those two numbers. Okay. All right, so what we're going to do on this next problem is kind of match a picture with the relationship of R. So for this first one, A, R is -0.83. So this is like a strong negative relationship. So I'm going to look at these answer choices for a strong negative relationship, and I'm going to say this is A. All right. For B, this is a strong positive relationship. So I'm going to look at these pictures and I'm going to say this is B. This is positive because we're going up. A was negative, it was going down. Okay, so for the next one, C, this is a positive relationship, but it's a little bit weaker. So between these first two graphs left, I could argue that this has some sort of positive trend, but it's pretty weak. So I'm going to say this is C right here. All right, for this last one, D, this is pretty close to 0. So this is close to no relationship or an extremely weak one. So I'm going to say this is D. The points are kind of scattered about. There's no real trend. So there you go. All right, so the next thing we need to do is learn how to actually solve for that value of R, okay? And here's a formula to solve for R. Okay, for that Pearson correlation coefficient, this is how we solve for it. It looks pretty crazy. It's the longest formula we've had in statistics so far this year. We're going to use a table to help us organize that information and do some examples. All right, okay, so here we go. We're going to determine the correlation coefficient given the age of a person, which is X, and their glucose level, which is Y. All right, so here's our X's and here's our Y's that's given to us. Okay, step 1 says create a table with the X and Y values, make room for 3 more columns in the table. And so we're going to do that now. We're going to multiply X times Y, which goes here. We're going to square X, which goes here, and we're going to square Y, which goes here. This is tedious, kind of like when we first learned how to find the standard deviation. So take your time with it, use that calculator. I'm going to fill out my table here. It'll let me. Okay, here we go. Sorry about that. All right, so for this first value, I'm multiplying the X's times the Y's. So 43 times 99 is 4,275, and on and on. All right, for this next column, I'm taking the X value and I'm multiplying it by itself. So for this first spot, you know, X squared is 43 times 43. All right, and that gives me 1849. And I'm going to keep doing that. So 21 times itself is 441, and so on and so forth. All right, and then for this last column, we're doing the same thing, but we're taking the Y values and we're squaring them. So for this first one, it's 99 times 99, and so on. All right, there we go. All right, step 2, we actually already did that, complete the 3 other columns. We've done that. Okay, so step 3, now we're going to add every column. So just as a refresher, this symbol right here, this is a sigma symbol. It means add everything up or find the sum. Okay, so that's what we're doing. We're going to add up all these X values, and then that number is going to go right here. We're going to add up all the y values. All right, and that goes here. We add up all the x times the y. We add up all the x squareds. And then we add up all the y squareds. All right, we double check that and we're good to go. We need to know the value of n. So that's 1, 2, 3, 4, 5, 6. So n is 6. Okay, and we're going to plug everything into this formula. All right, so here we go. R equals n, which is 6, times the sum of xy, which is 204.85, minus the sum of x, which is 247, times the sum of y. All of that gets put over a big square root. All right, n, which is 6, times the sum of x squared, so this 11,409, minus the sum of x, which is 247, to the second power. All right, then we have n times the sum of y squared, minus the sum of y, which is 486, squared. Okay, so now I'm going to go to my calculator. I'm going to do 6 times this 20,000, then 247 times 486, then I'm going to do 6 times this number here, I'm going to do 247 times itself, or to the second power. All right, and then 6 times 40,000. And then 486 to the second power, or times itself. Almost done here. All right, I'm going to subtract these numbers in the numerator. I'm going to subtract these. And I'm going to subtract these. All right, now I'm going to multiply these together and take a square root all in one step. So I'm going to multiply these two numbers and then take the square root. All right, I'm going to hold on to 4 decimal places, and then I'm going to divide. All right, we usually use 3 decimal places for R. So since this is a 9, I'm going to round this up to 0.530. All right, and there's your process. All right, so now we're going to learn how to test to see if, if that R value is significant. Does that actually mean anything? Okay. So, the closer R is to 1 or -1, we know that's a strong relationship. The question is, how close does it need to be in order for this to be significant? Okay. All right, so we have a critical value right here, this subscript alpha. We've seen that before. All right, and there's a table to find that critical value. All right, and if I just go to the last page of notes here, here's our critical values for R. Okay, so we have a value for N, we have two different levels of significance, 0.01 or 0.05. So these are going to be our critical values. All right. So we're going to determine if R is statistically significant. So for this first one, I have a level of significance of 0.01 and N is 11. So let's look here. So N is 11. Level of significance was 0.01, so that's 0.735. Okay, now right here, our level of R was 0.731 and our level of significance was 0.735. So it is statistically significant if the absolute value of R is bigger than the critical value that we found. In this situation, it's less than. Okay, so we would say this is not significant. This absolute value here just means make it positive. All right, so for the next one, our level of significance is 0.05. So we're back to where N equals 11. This time we're 0.05, so that's 0.602. So we're going to compare R to our critical value. This time it's greater than, so now I would say this is significant. All right, I'm going to do a separate video for that last example.